How's it going, ladies and gentlemen? Mr. Donnie here looking at 9.3 problems. All right, it has to do with molecular shape and molecular polarity. You got to remember that molecules are going to be polar if they're polar bonds and have one or less lines of symmetry. If they have multiple lines of symmetry, the molecule is going to be nonpolar. So looking at the first one of the molecules below, only blank is polar. What you're going to have to do is first draw all of the Lewis structures for these things. And I'm going to cheat and do the movie magic and just kind of write what they are without showing you the steps, because I can do that. All right. And then there's no lone pairs of electrons around this, which makes it a symmetrical molecule, right? My drawing kind of sucks to see it, but you can cut it in half more than one way and it'll be symmetrical, right? So this is going to be a nonpolar molecule. ASH3 is going to kind of look like NH3, and it's only going to have one line of symmetry. It's going to have those lone pairs of electrons here. You can only cut it in half down that way, which means this will be a polar molecule, right? So B is looking good. Let's check out the other two. Whenever you have like a diatomic molecule like I2, it's just gonna, there's no way that's polar. Non-polar bonds, multiple lines of symmetry, definitely not C. SF6 is going to be a perfectly symmetrical molecule as well. It's going to be octahedral, and it'll have no lone pairs of electrons around that sulfur, so you can cut this in half a bunch of different ways, right? So it's going to definitely be nonpolar. CH4, you should probably get sick of seeing because it's the go-to molecule for structures to be drawn, and it's got, you know, a million lines of symmetry, so it's definitely nonpolar. So ASH3, because there's only one line of symmetry, is polar. 9 of the molecules below, only blank is nonpolar. So now they're saying that only one of these is nonpolar. Well, I'm going to, again, jump the gun and point out that water, you should know, is polar. Water is a polar molecule, so you probably don't even need to write that out. You should just know. NH3 is a polar molecule because it only has one line of symmetry. Right? It's got a lone pair of electrons up there. You can only cut it in half one way. That's definitely polar. HCl is a linear molecule with only one line of symmetry, so it is polar. TeCl2 is going to be the same shape as water. It's going to be a bent shape, which means it only has one line of symmetry, so it is polar. Now let's check out CO2. We got a total of 4, so that gives us 16. So we put carbon in the middle, and we put oxygens around the side, right? And hopefully you've seen CO2 enough to know that there's a double bond between carbon and the oxygen right off the bat. But let's show the steps in case you didn't. So we place all the electrons around. We've placed all of our electrons, but we see that the formal charge on oxygen and carbon is not good. Carbon is, what's it, +2, and each oxygen's formal charge is -1. Well, how can we fix that? With some multiple bonds. So we know, all right, well, carbon doesn't have an octet, right? And oxygen has 8, so it can be like, hey, why don't I just throw in some more? And now everything's happy. Right? Let me draw this better. Ah, crap, got rid of it. Gone. Come back. Right? So it has multiple lines of symmetry, which means it is nonpolar. 10. All the molecules below, only blank is polar. All right, again, some movie magic. All right, this isn't a Lewis structure tutorial. It is a molecular polarity tutorial. So I'm just going to quick draw out all the shapes. This is CH4. This is SEF4. All right, it's going to have a lone pair of electrons. And then SiCl4 looks like this. No lone pair of electrons on that center element. All right, so this has multiple lines of symmetry, so it can't be that. CH4, again, also has multiple lines of symmetry, so it can't be that. SEF4, because there's this lone pair of electrons, really only has one line of symmetry, so it is polar. SiCl has multiple lines of symmetry, so it is nonpolar, so it can't be that. That's good choice C. All right, 11. Again, I'm going to just quick draw the structures, and I'm kind of omitting the outer elements with their whatchamacallits, unshared pairs of electrons, because we're not really interested in those. We're interested in what's going on in the central atom. But this is what you should get when you draw the Lewis structures. All right, so now, oh, I forgot two, right? Cl2 and BeCl2. So those are all the Lewis structures. So now testing them, see which ones are polar. Well, CCl4, like we said before, has multiple lines of symmetry, so it's nonpolar. BCl3 has multiple lines of symmetry as well, so it is nonpolar. NCl3 only has one line of symmetry because of those lone pairs of electrons, so that's definitely polar. BeCl2, you can be cut down in the middle and cut down in the middle the other way, so it's nonpolar. Same with Cl2. Yeah, cut it in half, nonpolar. So choice C. 12. Which of the following molecules has a seesaw shape? All right, well, again, I'm going to run through the Lewis structures. PCl3 is going to look like NH3. It's going to be that same shape. CCl4, we've done enough times already, even in this chapter, to remember the shape of it being tetrahedral with no lone pairs around the carbon. TeCl4 is going to have one lone pair of electrons around that central atom. So that's going to change its shape from whatever it was to something else. XeF4 is going to have two lone pairs of electrons around that central atom. Right, and then what's the last one? SF6. It's going to be no lone pairs of electrons around the sulfur and 6 fluorines all around it. So let's figure out what shapes are going on. Well, with PCl3, we have 4 domains, one of which is a non-bonding pair of electrons. So that's going to be trigonal pyramidal. Right? It's going to look like a tetrahedron, except the top's been cut off to a point. So it's going to be a triangular base, right? Going up to one point like a pyramid. So that's trigonal pyramidal. CCl4, tetrahedral, all right? That's a shape that you've seen millions of times, including Regents Chem. This one here, TCl4, is a little different, isn't it? It's got 5 domains, so its electron domain would be trigonal bipyramidal. But because one of those electrons is gone, or one of those bonding domains is just a lone pair of electrons, it changes its shape to the seesaw. Right, so this would be seesaw. And it's kind of funny, right? Like seesaw, yeah, that's a science term. No, really, it is. Now, XeF4 would have been octahedral, except it's got these 2 pairs of electrons that are unshared around it, which is going to make it square planar. And then SF6 is octahedral. So correct answer would be C. Which one, seesaw? That one. All right, I hope you found it helpful. See you in class.